Thank you. So we have heard quite a lot at this conference about microcosmos, about accelerators, and indeed about philosophy. So now I turn to the first N in MMAP, the macrocosmos. And I should say that this talk is in honor of our host, Professor Vikas Sinha, who has not only contributed, as we have heard in many previous talks, to India's engagement with the microcosmos, with accelerators, and indeed philosophy, but he has also been an inspiration for work that has been carried out here and other places in India in cosmology. This is less well known, but in fact he was the driving force behind the setting up of a Center for Cosmology and Astroparticle Physics here, which has active involvement in the dark matter experiment Picasso, in gamma ray astronomy, both at the Indian laboratory in Hanle, and perhaps also in the forthcoming Cherenkov telescope array. So I've known Vikash now I thought about it it's about 46 years, because that is when in 76, he stopped his car on Hoyuhawa Road to give Mandy and me a lift. That was our first encounter, and it has really been a pleasure. And having your encouragement has been very important for the work I'm about to describe. Because this is not going to be perhaps the usual cosmology talk that you have heard. It's going to be a little different. So I'm going to talk about going beyond the cosmological standard model. So let's start by talking about what is the standard model. That of course depends on what era of history you are talking about. So every culture has its own cosmology. I mean, the Aboriginals of Australia, a 40,000-year-old cosmology. In Hindu mythology, there is a cosmology which is quite different. So if you talk about European cosmology, they had a standard model that reigned for 2,000 years, starting with Ptolemy and Aristotle. And you can see here how that looked. This is actually from Kante Aligari's book, and it describes let me get this right. Oops. So I'm trying to figure out what the reason is. Anyway, is it the right one? Is it one? So as you can see here, we are at the center of the universe where we of course belong, and the ancients recorded the sky exactly as we see it. We see the orbits of the moon, the sun.
Full screen.
Oh yes, I'm sorry. Thank you. Oh. No, it's not sorry. Fine. So you see the orbits of the known planets, and then At the end, you see what they call the prima mobile, the crystalline sphere where all the stars are fixed because they don't move on the sky. In fact, Dante actually describes a strange phenomenon. He says, beyond the crystalline sphere, there are converging rays of light ending in a big glob of fire. And interestingly, that is a very accurate description of the hypersphere that is our modern cosmology, where that would be the cosmic microwave background. But let's come to that in a minute. Now this, as I said, held sway for 2000 years, and then there was the Copernican revolution. But all that really did was to simply change the actor at the center from the Earth to the Sun. And this is the system which we still use, in which we reduce cosmological data. We reduce it to the heliocentric frame, correcting for the Earth's motion and spin and so on. And this has, of course, been supplanted when we go to cosmology, because about 400 years after Copernicus, when we constructed the first cosmological models, how do I get rid of this? What? Oh, right. Let's see. I thought you meant I should hide. So the first cosmological models were constructed shortly after Einstein came up with his general theory of relativity. And we actually are celebrating the 100th year of the publication of Friedman's 1922 paper, which he in fact wrote in 21. It took a year to get it published. And this Copernican principle was extended in their work to demote the sun also from being the center of the universe. And that is because you have to realize that in cosmology, everything that we observe is along our past light cone, and we have a particular vantage point in the universe. We cannot move somewhere else in the universe and look from there to see if we see the same thing. So therefore, an element of philosophy is essential in cosmology. You have to adopt a principle, and that principle is called the cosmological principle. It was formulated in its modern form by Edward Mill, who was the Rouse Professor of Mathematics at Oxford, the chair that Roger Penrose held subsequently. And it just says something that you might agree with, that the universe must appear to be the same to all observers. There is nothing special about us. So it's a extension of the Copernican principle. Now, because of this limitation, it is always necessary to make this assumption in order to be able to say something about the universe as a whole, based on observations made from our particular vantage point. And I emphasize this because the rest of my talk will be about testing this cosmological principle, which we have only been able to do in the last 5 or 6 years, because the data was simply not there. The first cosmological model was constructed 100 years ago without any data. At that time, we did not even know that we lived in a galaxy, far less that there are 10 billion other galaxies. Nevertheless, based on that, the same equations for the standard cosmological model, we have now come to the modern version, which is now in color rather than black and white. And this is from the NASA drawing office. And what it says is that our expansion rate is currently accelerating, as if driven by the cosmological constant in Einstein's equations. And astronomers tell us that they know the makeup of the universe very precisely, and that the part that we are made of is only a few percent normal matter. We know this from Big Bang nucleosynthesis. And there is about 6 times more matter that gravitates but does not interact with radiation, dark matter. But most of the rest of it, here it says 74%, somebody else says 73%, it's of that order, is what's called dark energy. And that is believed to be the energy of the vacuum, but at a ridiculously small scale of a milli-electron volt, because it actually is the product of the Hubble parameter square and the Planck mass square, which is a measure of the weakness of the gravitational coupling. It's 1 over 8 pi g Newton. And that gives you, therefore, a scale which is intermediate between 10 to the minus 42 GeV, which is H naught, and 10 to the 19 GeV, which is M Planck. And it is this model that has become the standard model of cosmology. And astronomers think it's a simple model, the same way that previously people thought that the Ptolemy-Aristotle model was simple. Of course, you had to put in epicycles of the planets to fix it when the data came along, but and at some point we sort of threw it all away. But it wasn't because the data did not fit the epicycles. You didn't need many epicycles. I've been told this by Arvind Gentry, who is a professor of the history of astronomy at Harvard, that it's a myth that the epicycle thing was abundant because it didn't fit the data. It actually fitted the data better than the Copernican model when it first came along. The reason we abandoned that was because there was no dynamics in it. There was no underlying physical understanding. And I think the same is true today. We have this model which is said to be very successful, but it has no physical foundation at all. And what has happened is that we have had lots of missions on the ground in space. Here we have various things, the MMAP satellite from NASA, this is Euclid, this is the Planck satellite, there you have the Sloan Digital Sky Survey, here you have the, this is DAISY, I think, a telescope which is on the Kitt Peak National Observatory at Mayal. And this is a telescope being built in Chile right now called the Vera Rubin telescope, which will conduct what is called LSST, Large Legacy Survey of Space and Time. But all these experiments, which have cost the same kind of money as large accelerators do, are just measuring the parameters of the standard cosmological model in what is come to be called precision cosmology. But they are not checking the fundamental assumptions of the cosmological model in the way that we have done for the standard model of particle physics. We did it at length. We measured the radiative corrections to very high precision and tested that the gauge groups are indeed what they are meant to be, tested that the particle content is indeed what it's meant to be. That has not been done in cosmology. So that is the lacuna that I intend to address. Now, let me first tell you what the standard cosmological model is very briefly. So basically, you assume the simplest possibility for space-time metric. So that is the Friedman, Robertson, Lemaitre, Walker metric. And for the dynamics, you adopt general relativity. And for the content of the universe, you assume ideal fluids. This is how you construct a cosmological model. And basically, this picture shows you what the universe looks like. Imagine you are sitting at the north pole of a sphere and you're looking down. And the Big Bang would then be the south pole. Light is constrained to come to us only along the surface of the sphere, which is how a singular point can occupy your entire horizon here. But the light cannot just come to us directly, because as you go back in radial coordinate, which is actually conformal time or redshift, which is marked here, so the universe was a factor of 2 smaller than it is here. It was a factor of 1,000 smaller here, and here it was infinite times smaller. So be careful, it's a very interesting scale, very compressed. So we see the initial singularity filling our sky, and the photons from there cannot come directly to us, because once the universe is hotter than 1,000 times today, the matter gets ionized, it becomes a plasma. So the photons have to random walk through it in the same way that photons have to random walk out of the sun. So it's like we are inside the inside-out sun. And the photons only can come to us from this surface called the last scattering surface, where the universe becomes transparent, and then they come to us. And most of cosmology has been done within this redshift of a few. The highest redshift objects today that we can see in telescopes are at about 10. There is a record holder announced every day. But then there is a so-called dark ages, where nothing is seen, up to the redshift of 1,000, where you see the cosmic microwave background. Interestingly, 2 points on the last scattering surface that are separated by a degree, they have their past light codes just about in causal contact at the initial singularity. Points which are further apart are not in causal contact. And the big mystery of cosmology is to explain why the sky looks so uniform given this space-time structure. But here is the metric which I've written in terms of this conformal time, which is the usual time coordinate divided by the scale factor, which is the only dynamical factor in this metric, to keep it simple. And this was, of course, perfectly justified when you start out trying to construct a model of the universe. And then when you use this metric to construct the Riemann tensor and construct from it the Ricci tensor and the Ricci scalar, which are these quantities that you see here with these subscripts. So these have 2, the Riemann tensor has 4. Therefore, you have made an enormous simplification to actually enter this metric to construct these guys here, and then you can relate the geometry of the universe to its content, which is parameterized here in terms of the energy momentum tensor. And the correction factor is, of course, Newton's constant, 8 pi g, which particle physicists like to write in terms of the inverse of Planck mass square. So what you then have is the crucial assumption of homogeneity and isotropy that allows you to write this metric, allows Einstein's equations, which are 10 equations because it's a 4 by 4 matrix, but it is symmetric, so there are 10 independent equations. And that simplifies to just one, which we call the Friedmann-Lemaitre equation, which tells you how this scale factor evolves with time, governed by the energy density, matter, the curvature of spatial sections, and a cosmological constant. And what we can do is to divide this equation through by h squared, and then I can write it in terms of the present-day Hubble parameter and the fractional energy densities in matter, curvature, and lambda, which are defined here as so, in ratio to the critical density. So the bottom line of doing all this is that you get a sum rule. It says that omega matter plus omega lambda plus omega k add up to 1. Why does this simple sum rule come from? It comes from this assumption of homogeneity and isotropy. And if I now give you away the punchline by saying all our evidence for lambda comes from this sum rule. We do not measure it directly. We only measure curvature directly and the matter content directly, and we infer lambda from the sum rule. So if this sum rule is not the whole story, if there are additional terms there that you have not written down or allowed for in our framework, then we'll go wrong in inferring it and saying that the universe is dominated by vacuum energy. The point of this exercise is, of course, to illustrate to you that this was done at a time when we thought that energy momentum tensor was just dust, non-relativistic particles. Like dark matter, it's just non-relativistic particles. But of course, in the 1930s and 40s, when we realized that the universe is actually made out of fields, not particles. Particles are just the excitations of those fields. And Pauli and Zeldovich and others realized that the energy momentum tensor also has a constant piece, which are the vacuum fluctuations of these fields, and they must add to the lambda that comes from the geometry. So this arises because this term is there because of general coordinate invariance. That term must be there. It is not Einstein's choice or anybody's choice. But that term must then combine with the term that is coming from the fields to yield the lambda, the capital lambda that is entering into Friedmann-Lemaitre equation. And these two terms, I emphasize, know nothing about each other. This is completely arbitrary. This guy is determined by the quantum fields in your energy momentum tensor. And yet, they sum up together to create the quantity that will have an effect on cosmology. And I highlight that omega lambda is lambda over h naught squared. So therefore, if omega lambda is of order 1, that means lambda is of order h naught squared. This is the only dimensionful quantity that I have allowed in my metric. And therefore, inevitably, any measurements that I make to infer lambda by this procedure will give it a value of order h naught squared. I need not remind you that h naught is nothing fundamental. It is just the current rate of expansion of the universe. It changes with time. And yet, this has become our standard model of cosmology. Now, I have highlighted how the lambda arises there, but let us now move on to asking what the effect of this lambda is. And the effect is, in fact, because it has negative pressure, because of the Lorentz invariance requirement on the energy momentum tensor, the pressure term has to be negative of the energy density. And therefore, the second equation of Friedmann and Lemaitre says that this quantity can become negative, and therefore the rate of change of the scale factor velocity, that is to say the Hubble parameter, can also be positive. The universe expansion can appear to accelerate. Now, what does the standard model of particle physics that we are also proud of say about this? Well, I have written it here in a very symbolic form. So we have the gauge fields, I've just called them F. We have the fermions, which I've labeled as psi, and we have the Higgs, which is phi. And I'm just showing you the renormalizable part of the Lagrangian. You can, of course, add an infinite number of non-renormalizable terms, which will give you the new physics like neutrino mass or proton decay or flavor changing currents, etc. And we have recently, as you know, found the Higgs, and the race is now on to determine its exact potential, which we usually model by some Mexican hat like that. But we know it's self-coupling, and we know the vacuum expectation value from muon decay, so we know quite a lot about it. The point is that this Lagrangian and its symmetries allow of two terms, which are so-called supernormalizing. And those two terms, one has attracted the most interest in the last 40 years amongst phenomenologists, is the fact that if this Higgs is really a fundamental particle, it couples to everything in the vacuum. And therefore, in particular, for example, it will couple to the top quark in the vacuum. We need not invoke granularification or anything else. Let's just look at the coupling to the top quark. That mass correction will go as the square of the cutoff of the theory, the scale up to which we consider the standard model to be valid. It's a quadratic divergence, and HT is, of course, the top quark coupling. So just the fact that there is one particle in the standard model heavier than the Higgs already spells disaster, because the Higgs is not protected by chiral symmetry as the electron, for example, is. So the electron mass can be quite close to zero. We understand that by letting it go to zero, we see chiral symmetry. By Jove's criterion, a quantity is naturally allowed to be small if letting it go to zero shows you an underlying symmetry. Here there is no symmetry. And therefore, this quadratic divergence of the Higgs mass has occupied us and led to an explosion of beyond standard model physics, which is, for example, so the symmetry at the V scale or compositeness. Compositeness took a big blow at length because we did not find any evidence of the large radiative corrections that would have been expected had there been compositeness. But we still cannot honestly say that the Higgs is fundamental. It's just a matter of how well we look at its couplings, which is why for the next 10, 15 years at the LNC, that is the main program, to measure the Higgs properties, if possible, to percent level, and on the same grounds, theoretical calculation